Welcome back. In this video, we're going to look at an example and see when to use which unit vectors and how we might combine them to find the answers that we're looking for. So given this problem setup, what we have is a cannon that's going to shoot some particle that we can treat as a particle, and we're going to know some information about it from the firing position, that is its muzzle velocity, that's the velocity right when it leaves the cannon, and the angle that we're firing at. So given that we know it's going to travel some parabolic path, because all free flight objects do, then let's find some information about that. So information like, what's the maximum height that this particle is going to ever reach? And we're going to call that at point B, the height of its, the highest point it's going to get. And then what is the radius, what is the maximum distance that that thing can travel, that particle can travel? And then let's look at the radius of curvature of the particle as it's passing through. So those are two different types of information, and we'll use different unit vector systems to find out that information. So let's go ahead and begin. So given what we know, we want to find the information. Let's work on a solution process. Well, first of all, let's look at these first two, maximum height, maximum distance. These are things that make sense in a global reference frame. So let's go ahead and use our Cartesian or our XY coordinates to determine those. So the first part would be height and distance, which we're going to use our rectangular or our Cartesian coordinates. So these are going to be our XY coordinates. So let's deal with the height part first. So we know that the velocity in the y direction is going to be equivalent, or at least the square of it, will be equivalent to whatever initial velocity we have in the y direction squared. And then I'm going to go ahead and know that acceleration is downwards, and it's a value of g, which is gravity negative 9.81 meters per second. So I'm going to use -2 times g and the change in y from one place to another. So let's go ahead and calculate that as the total height. Well, what do we know about this problem so far? We don't know the height, that's what we're looking for, and we don't necessarily know this velocity at the height, but we can determine what this initial portion of that velocity is, right? So the initial velocity in the y direction needs to be the velocity, the total velocity, and then we're going to have some angle, right? So we've got some velocity, and we're going to have some xy components of this. So if this is our theta angle, then our Vx would be our V cosine theta, and our Vy, the upwards portion, would be V sine theta. All right, so that tells us that V is V sine theta. And what is the velocity in the y direction when it reaches the very top of its path? Well, that's 0. So 0 squared, and then V sine theta squared minus 2g times h. We can use that to find out the height that's going to be traveling. So put the 2gh on the other side if you like, and then subtract out the 2g. If you do that, you'll find out the height that it can travel, go from its maximum velocity in the y direction to 0. That height it's going to travel, given that g is 9.81 meters per second, and our velocity is our 20 meters per second. If you calculate that through, you'll find out the maximum height is about 5 meters. It is 5.09 meters. All right, so that was pretty easy for the first part. Now we can figure out how far of a distance it's going to travel. So we know our distance functions, or our x portion, as the x position is whatever initial x we're at, plus the velocity in the x direction, times time, And if we had any acceleration, we would put it here, but we don't have any acceleration in the x direction. So now we've got a problem though, because we've got two parameters, x, which is what we're trying to find. We can go ahead and set our coordinate system at 0, so that gets rid of that one. But now we have a function of time, so how long did it take to get there? We don't know that one just yet, but we know that however much time it takes to travel in the y direction has to be the same amount of time it travels in the x direction. So we could do this a couple of different ways. I'm going to do it this way. We could also say that the y position is a function of the initial y position plus the velocity in the y position times time minus 1/2 the acceleration, which is g. So I'll go ahead and say 1/2 g times time squared. And now we've got a function that tells us something in time, but it's not the easiest one we could use. We could also say that the velocity of y is whatever the initial velocity was in y plus the acceleration component, which in this case will be minus the acceleration minus g times t. So this one is much easier to allow us to calculate what that initial time should be. So let's do it in this way. If we know that at the height that the particle will travel at point B, that we can define the time as its initial velocity minus gt. That allows us to define a value of t that is the initial velocity in the y direction divided by gravity. So what time is that? That's the time it takes to get up to the top part. And if you do calculate that, that's about 1.02 seconds. But notice that's only the time it takes to get up to here. So the time to get all the way back down, so the time to go from here to here is 1.02. So therefore, the time to get all the way back down is that our t needs to be twice that, or 2.04 seconds. And now we know a t value. So if we come back in and plug in our initial velocity, we can find a total distance x that it will travel. And if you plug in those values, you can do that yourself. You should get about 35 meters. So I have 35.33 meters. So now we've answered two questions. What's the maximum height it's going to achieve? And what's the maximum distance it's going to travel? And along the way, we also found out how long it's going to take to get there, which might be an interesting information if you happen to be on this side of the cannon and you want to run away. Now, the next part is the radius of curvature. Now, that's a key word for us, and it means that we're going to need to look at a different set of unit vectors. So the radius of curvature portion it turns out to be pretty easy if we think of it in two different portions. So let's look at A. At point A, which is right as it's leaving the cannon, we know that the particle has some acceleration that's down. That's the only thing it's going to be accelerating with some gravity. And then it's going to have some normal component and some tangential component. So that normal component will act towards that radius of curvature, and then it will have some tangential component. So those are our two components that we know about. Now, based on the angles here, since we know this is theta, based on, if you do a little bit of trig, you'll find out that the angle between these two is also that same theta. So it's also going to be 30 degrees based on how these angles are set up. So we know that the normal acceleration is equal to the velocity squared over the radius of curvature. That's a definition that we know from how we've defined these types of unit vectors. And now we can see that at A, the normal portion of acceleration can be defined as a function of the gravity and that cosine. So it's also equal to gravity pulling in a downwards direction. So we can go ahead and use our negative gravity if we like. And then it's going to be the cosine portion of that angle. So notice what's powerful about the tangential and normal components is that if we know velocity, then we can find these things pretty easily. So velocity as an input is known, so that's 20 squared. And then our normal component of the acceleration is the gravity, but only an angle portion of it, cosine 30 portion of it. And that allows us to find out a radius of curvature, rho, that is equal to about 47 meters. It's 47.08 if we want to be specific. So that's the radius of curvature at A. And now we can think of the radius of curvature at B. Well, first of all, is the question we should ask ourselves, is the radius of curvature constant? Maybe it is. So let's think about it. At B, we now have the situation where the particle only has an acceleration in the normal component, straight down, and that also happens to be exactly gravity. So it also happens to be the same thing as the total portion of it. So when we put those things together in the same frame, we know that now we've got gravity equals the velocity squared over our radius of curvature at B. Now our radius of curvature at B is what we're trying to find. And what we don't know is what is the velocity of this part when it's at B. Well, we know that from our rectangular components, when we talked about this at the height here, that there's no velocity in the y direction. And the velocity in the x direction, there's nothing to change it. So it has whatever it has from the beginning, since there's no positive or negative acceleration. Therefore, it must be the same. So therefore, our velocity at this point must be our velocity in the x direction, which we can calculate from the cosine portion. Velocity in the x direction squared divided by our radius of curvature at B. And when you put the velocity of 20 times the cosine of 30 squared and then divide out gravity, you get that the radius of curvature is now about 30 meters, 30.5. So notice that the radius of curvature isn't constant. And if you had taken a guess before when I asked, do you think the radius of curvature stays constant? Hopefully you said no, because of course it's not. It's a parabolic shape. So the only thing with a constant radius of curvature is a circle, because that's what it has, a constant radius. Any other shape will not have a constant radius of curvature. So that radius of curvature here is going to be longer because that arc is wider. And then at the point of our parabola, it's a lot tighter of a curve. So of course that radius of curvature has now shrunken in quite a bit. And it's going to be entirely dependent at what angle we shot and what the initial velocity is in order to figure out what those particular angles are going to be. So far in this problem, we've used our rectilinear components, or our Cartesian components, and we've used the normal and tangential components, although really we've only cared about the normal. It's allowed us to find everything we wanted to find. Now our question should be, when and how would we use the transverse and the radial portion? Well, the transverse and the radial portion would be an interesting problem. It's a little more complicated on free flight motion than some others, but there's a very good example of when we'd want to do it. So say we put a person who is a little spotter here, and they've got some glasses, and they're going to be watching this particle. And in their glasses, they've got very good computation so that they can find these things. Then they're going to be able to say, I know how the current position is, and I know the current angle theta that I'm seeing this object at. And if I've got some calculations or computers going on in there, I can also find information like r dot, theta dot, and r double dot, and theta double dot. And this type of information, which you can find from observing that particles, the little spotter sees the thing going by, that type of information can then be used to find the functions of velocity and acceleration at any point that we want to along that path. So that one's a little bit more complicated in that the R function for the parabolic path has got several sines, secants, and tangents going on in there. So I'm not going to do the math on that side, but that would be the type of application that we would be interested in knowing how to find velocity and acceleration of the particle, given that, say, we're measuring it from a particular location and there's some distance and changing in theta. So if you see keywords like it's this far away, it's 5 kilometers away, and the rate of change of the angle in that measurement is this, then that's telling you that you're probably going to want to use the radial and transverse components in order to find out the information that you're looking for. So to recap, in this problem, we looked at the rectilinear and the normal and tangential components in order to find information that we wanted based on what was asked. And we didn't really need to, but I explained how we might want to use the transverse and radial if the situation was maybe an observation type of position.